Okay, so as I said before, there's been a quest for finding larger and larger prime numbers. Okay, so for almost 300 years, the largest prime known has been of this form, like a power of p minus 1, where p is also prime. And these have a special name called Mersenne primes. So there is an extremely efficient test to check whether 2 to the power p minus 1 is prime. So this form for prime numbers is a good one in the quest for finding larger and larger primes. And also there's actually a test for computer efficiency that's done to see if like you have a computer system and you get it to find a known large Mersenne prime, and that kind of tests how efficient your computer system is, how well it's working. So these are kind of have really practical applications. Okay, so let's look at a few examples and decide whether they're Mersenne primes or not. So we're just going to look at some small Mersenne primes, and we're not going to write a computer program. We're just going to test them by hand. All right, so part A, we're looking at 2 squared minus 1. This is 4 minus 1, which is 3. So yes, this is a prime number. 2 cubed minus 1 is 8 minus 1, which is 7. This is also prime. 2 to the 5 minus 1 is 32 minus 1, which is 31. Also prime. 2 to the 7 minus 1 is 128 minus 1. 2 to the 7 is 128, right? I think so. 2 to the 7 is 128, yeah. Which is 127. All right. That I don't know, is that prime? Let's see, if I do square root of 127, I get 11 point something, so I gotta check up to 11. So 127 doesn't divide by 3, by 5, does divide by 7, no. Doesn't divide by 11, no. Yep, that's prime also. And E, let's check 2 to the 11 minus 1. I think 2 to the 11 is 2048 minus 1. 2048 minus 1 is 2047. All right, let's do this by trial division, figure out if this is prime. So square root of 2047 is approximately 45.2. So let's divide. So I'm not going to show the divisions, but I'm going to divide by, doesn't divide by 3 or 5. Let's check 7. Nope. Check 11. Nope. Check 13. Check 15, 17. Check 19. Next one is 23. Oop. Wow. 2047 is actually 23 times 89. So this is not prime. 3 times 89, look at that. Cool. I was ready to go all the way up to the prime that's slightly lower than 45, but it is 23 times 89, so this one is not prime. Okay, so just because it's in that form, it doesn't make it prime. What this is saying is that a lot of the large prime numbers take that form. So even if it's sort of your where this power right here is prime, so that can't be composite. So if you're kind of questing for a large prime numbers, that's a good form to start with, but then you still have to develop an algorithm, or there is an efficient test to check whether this is prime, not trial division, because that takes forever. So this is an interesting problem to take on as a mathematician or a computer scientist. So there are a few prime number theorems and conjectures that basically are designed to help people find prime numbers. So we're talking about the Mersenne primes just in the last example there, and I sort of Googled and found an article. Let's see if I can bring it up here. No, just a sec. Okay, so here's a Wikipedia article on the largest known prime number as of January of this year is 2 to the power 82,589,933 minus 1. So it is a Mersenne prime number. And it basically has over 24 million, almost 25 million digits when written in base 10. So it was found by this guy of the great internet Mersenne prime search. There's a program called GIMPS in December of 2018. So there's this program here that kind of encourages people to write programs that find the next prime number. And I think there's like a cash prize associated with it. Like they offer $30,000. No, $3,000. That's not much, but it's great. Research Discovery Award for participants who download and run their free software and whose computer discover a new Mersenne prime having fewer than 10 million digits. So so there's a few prizes and sort of foundations that that kind of encourages this. Okay. Cool. All right, so there's some kind of conjectures and theorems made up about prime numbers. I'm not going to go and prove any of them. I just want to mention them. So the prime number theorem says that the ratio of the number of primes not exceeding x and x over ln approaches 1 as x grows with that bound. Okay, so log of x is the natural log of x. So we can use the prime number theorem to estimate the odds that a randomly chosen number is prime. So the odds that a randomly chosen positive integer less than n is prime is approximately n over log of n over n, which is 1 over log of n. So if you sort of pick any number, the odds of it that is going to be prime is this. So you can see that if the larger n gets, the less of a chance it will be that it's a prime number. Another kind of conjecture, so it's a conjecture, it hasn't been proven. It says that every odd integer n, if bigger than 5, is the sum of 3 primes. And also every even integer bigger than 2 is the sum of 2 primes. Okay. There's another theorem that says that there are infinite number of primes of this form, n squared plus 1. And the twin prime conjecture says that twin primes are primes that differ by 2, and there are infinite many number of twin primes. So these are sort of theorems that people have worked through through the years to kind of in this area. Okay. So I'm not going to prove them, they're just sort of interesting. You can sort of look them up to find out more information about them. All right, so a lot of the work that we're going to see in the rest of this chapter has examples, have sort of their basis on these sort of prime number relationships and theorems. So next thing we're going to look at is the greatest common divisor. Okay, so if we have two integers a and b and both not 0, the largest integer d such that d divides into both numbers is called the greatest common divisor of a and b, and we denote it by the GCD of a and b. All right, so for small numbers, you can sort of do it by inspection a lot of the time, right? So find the greatest common divisor of 24 and 36. GCD of 24 and 36. What's the largest integer that divides into both of them? It's going to be 12, right? So you don't actually need to do anything to figure that out. It's sort of just by inspection. Let's look at the next example. So find the GCD of 17 and 22. Oops, 22. All right, so 17 is prime and 22 is composite number, 2 times 11. So we can sort of, again, we can break things up. The 17 is prime, so it's just 1 times itself. And 22 is 2 times 11. All right, so this kind of leads us into probably a method that we know already for finding greatest common divisor, which is looking at the prime factorization of each of the numbers and kind of saying, oh, the GCD is going to be all the different prime numbers up to the highest power that they, to the lowest power that they appear, sorry. So this is going to be 2 times 11 times 17. So basically we ended up multiplying 17 by 22. Right, so 2 times 11 times 17. So this is sort of like a method that we've probably known since we were finding common denominator for fractions. All right. All right, so this definition talks about pairwise relatively prime numbers. Okay, so if we're dealing with 2 integers, you say that they're relatively prime if their greatest common divisor is 1. Okay, so in the last example, in the last example, right, I think I was not, the last example is incorrect, isn't it? Okay, so let's relook at this. Okay, so I think I found the LCM, not the GCD, did I? Okay. But yeah, let's revisit this. Okay, let me see if I can figure this out. Okay. All right, so if you look at the prime factorization of the 2 numbers, you notice that there are no prime numbers bigger than 1 that go into both 17 and 22. So the GCD of 17 and 22 equals to 1. All right, there you go. So let's look at the next example. Sorry about that. Okay, so we're talking about relatively prime. So yes, the 2 numbers in the last example were relatively prime to each other because they had no common factors. So the GCD is equal to 1. Okay, so pairwise relatively prime is useful if we're looking for more than 2 integers. You're sort of basically going to do all the pairings, and if all the pairings of the integers have GCDs of 1, then you are going to say that that set of integers is pairwise relatively prime. Okay, so we're going to do this example. Let's look at the GCD of 10 and 17. Right, so 10 is 2 times 5, and 17 is just 1 times 17. This should be a 5. There are no common factors, so the GCD here is 1. Then we're going to pair up 10 and 21. So 21 is 3 times 7. And no common factors between 10 and 21, so the GCD is 1. And then if I do 17 and 21, no common factors, so the GCD is 1. So between all the possible pairings of the 2 integers, they're all relatively prime in pairs. So you say that they are pairwise relatively prime. Let's look at this. So same question, but with these integers. So we're going to pair up 10 and 19. The GCD of that is 1. And 10 is 2 times 5, and 19 is prime. But if I pair up 10 and 24, the GCD is going to be 2, because 24 is 2 times 12, which is 2 times 2 times 6, 2 times 2 times 2 times 3. So I see that they have a factor of 2 in common. So these are not relatively prime. Okay, so no, they're not pairwise relatively prime, because for at least one of the pairings, the GCD is not equal to 1. Okay, let's look at this definition. So the Euler phi function, the Euler function, the value of the Euler function at the positive integer n is defined to be the number of positive integers less than or equal to n that are relatively prime to n. Okay, so let's find the value of the Euler function phi 15. Okay, so we're looking at integers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And so basically I just listed the numbers from 1 to that value of n to 15. And then I'm going to cross out whichever integers have a GCD that's bigger than 1, right? So it's because 15 and divides by 3, they're going to have factors in common. 15 and 5 are going to have factors in common. 15 and 6 have factors in common. 15 and 9 and 10 and 12 and 15 and 15 have factors in common. So all the ones I crossed out, it shares common factors with the number 15, but the rest are going to have a GCD of 1 with the 15. So I have 1, 2, 3, 4, 5, 6, 7, 8 left over. So phi of 15 is 8. Okay, so those are the number of positive integers less than or equal to n. They are relatively prime to n, and there's 8 of them in the list. Okay.